Today we're exploring the minimum height trees problem. Our goal is to try and find an optimized solution with minimum complexities of on time and on space. In this problem, we're given a tree consisting of n nodes labeled from 0 to n-1. The tree is represented by an array of n-1 edges, where each edge will indicate an undirected connection between two nodes. Our task is to select a root node such that the resulting tree has the minimum height among all possible rooted trees. A tree's height is determined by the number of edges on the longest downward path from the root to a leaf node. We need to return a list of root labels for all the minimum height trees. To give a visual example, LeetCode gives us some test cases. In the upper case, we'd be returning root labels containing node 1 in all four cases here. And in the second case, we'd be returning a vector with the labels 3 and 4. So, to solve this problem, there are four possible methods we can use for an optimal solution. They are A. Topological sort, B. BFS or DFS, C. Greedy, or D. Tree diameter calculation. I'm going to pause for a couple of seconds while you make your choice. So, for those of you who are able to get it, congratulations. And for those of you who just want to see the code, the answer here is A. Topological sort. We'll forego the brute force approach here and look at the optimized solution. So this optimized solution uses the topological sort algorithm to solve our problem efficiently. If we give a high-level overview, what we do is construct a graph from our given edges, like so, and then we call the topological sorting function to perform that topological sort. Eventually, we're returning the roots of all our minimum height trees. So how does this work exactly? Well, we take in the graph as input into our top sort function, and then we do the sort. We use the array incoming edges, or in degrees, to keep track of the number of incoming edges for each node. We start by adding nodes with only one incoming edge into a queue here. Our algorithm then iteratively removes nodes from the queue, decrementing the incoming edge of the neighbors, and add neighbors with only one incoming edge to our queue, once again. We continue this process until there are only two nodes remaining in the graph. Finally, once we've established our remaining nodes, we're going to add those to our result vector, which will then be returning. And this will represent the roots of the minimum height trees, and that's it. Now, let's take a look at the line by line in a bit more detail, starting from these helper functions. So first of all, typedef here, this is just defining the graph type as a shorthand for the 2D vector. addEdge, defined to add edges to the graph, is taking in our graph, our source node, and our destination node, and, well, we're adding corresponding undirected edges between these nodes. We'll come back to the top sort function in a minute, but first we'll look at our entry point to our solution. This is fairly simple. We're initializing a graph using n, which is our number of nodes. We're adding edges to it using the 2D vector we were given and the addEdge function. And then we're calling the top sort function to obtain the roots of the minimum height trees. The resulting vector will be returned by this, but once again I'll go into the top sort function in detail. The first thing we do in this function is initialize the variable nodes, and that's just the number of nodes in the graph. There is one interesting point here. If there's only one node in the graph, then that's what we're going to return as our result. You will remember that the graph nodes are labeled from 0 to n-1. If we only have one node, we're just going to return 0. After that, we're initializing incoming edges to keep track of the number of incoming edges for each node, which is fairly simple. And nested loops are used to iterate over the graph and count the number of incoming edges for each node and update the incoming edges array accordingly. The queue is initialized to store nodes with only one incoming edge. And then this is the critical part. We iterate over the incoming edges array and enqueue all nodes that have only one incoming edge. After that, our main loop begins, which is going to continue until there are only two nodes remaining in our graph. The variable sz is assigned to the size of our queue, so that it'll contain all the nodes with only one incoming edge. And we decrement the nodes count by sz, since we're going to be processing sz nodes in this iteration. We iterate through sz times to process each node in the queue, starting by getting the front node from the queue, storing it in this variable, and then popping. We then iterate over the neighbors of node I and decrement their incoming edge count. Once again, if the incoming edge count for a neighbor becomes 1, we enqueue it in the queue, like so. And that's pretty much it for our while loop. Once that's completed, we're creating the vector result to store the roots of minimum height trees. We then dequeue the nodes from the queue Q, pushing them into the result vector like so. And that's what we're going to return. We return our result vector, which contains the roots of our minimum height trees. And that's it. I hope that the breakdown has helped you understand the logic and functionality of each line in our code. For a more detailed explanation, I would recommend checking out the link. This is a Udemy course included in the description to the video. Dr. Ibrahim does a much better job of teaching the actual background and, well, how this can be applied using critical thinking to other problems too. In any case, for the purposes of our application, we're done. You should realize that to solve this minimum height trees problem, we can use a small variant on the topological sorting. There is an explanation included, and incidentally, there are explanations for the incorrect or suboptimal alternatives as well. If you'd like just to read through code to understand what's going on, we have it for you in C++, Python, and Java as well, all of which has been tested on LeetCode, and all of which will adhere to the method that is being shown as correct on the right. So that's everything for now. Thanks very much for watching. If you're following us on the Coding Card Sharp learning mode, the next card in this course is going to be the longest increasing path in a matrix.